this lecture series. So this is one of the first lecture of several lectures which will follow here. So these lectures will be on Revised Simplex Method. So understand the Revised Simplex Method, you have to understand the simplex method clearly. So therefore, it is very important that you have a working knowledge of the simplex method, then only you will be able to understand the Revised Simplex Method. So the first 2 lectures of this series will be dedicated towards the revision of the simplex method. So once you are adapted to the simplex method thoroughly, then we will be discussing the Revised Simplex Method. So let us not waste any time and move on with the topic of discussions. We will discuss the simplex method first. So simplex method, as all of you probably know it, that it's a process or it's a method of solving linear programming problems. Now, how do we solve these linear programming problems in using this simplex method? We start with the basic feasible solutions and then we iterate. And after each step, we check the optimality, if the solution is optimum or not. If it is not optimum, we again iterate until and unless we reach a solution which is an optimum solution. Now, how these solutions are optimum and how to test whether it is an optimum solution or not, and how to iterate, all this will be discussing, and also how to select the basic feasible solutions, that will be discussing. But you should understand few terms, that is, what is a basic variable, what is a non-basic variable, what is a slack variable. I think you should have an idea about all these variables. I am not going to discuss these variables here. Okay, we will move on with the problem. That will be very easy for you to understand. Mathematically, it will be difficult for you to understand. So let's start knowing simplex method using an example. So this is maximization problem. So all the problems that we'll be discussing here will be of maximization type only, because reverse simplex will be solving only maximization problem. So here the question is given that we have to maximize a function z, which is a function of 2 variables x1 and x2. So z is equal to 3x1 plus 4x2, and this we have to maximize, and this function is called the objective function, and this function is subjected to certain constraints, x1 plus x2 less than equal to 450, so 2x1 plus x2 less than equal to 600. So these are the constraints, and of course x1 x2 has to be greater than or equal to 0. So if we represent this in the canonical form, so I have introduced 2 slack variables s1 and s2. You can write it as x3 and x4 also, no issue. So you can introduce any variable name, but these are variables, are slack variables to account for the surplus resources. So in the first constraint equation I have introduced s1, and the second constraint equation I have introduced s2, and the coefficient of s1 in the objective functions will be 0 and coefficient of s2 in the objective functions will be 0. So it does not affect the objective function, but I have introduced so that to remove the inequalities. So here s1 and s2 also has to be greater than 0, obviously. Now we start with the initial basic feasible solution. Now what is this initial basic feasible solution? We start with the initial basic feasible solution that x1 and x2 are 0 and s1 is equal to 450 and s2 is equal to 600. So this is a feasible solution, and because it satisfied all the equations that is given here, but this is not an optimum solution, which we will find it out by testing whether this solution is an optimum solution or not. But obviously this will not be an optimum solution because z will become as 0. So we start with s1 is equal to 450 and s2 is equal to 600. Now here s1 and s2 are my basic variables, and x1 and x2 are my non-basic variables. So I construct the tables like this. So this is my objective functions on in the coefficient of the objective function cj. These are coefficients of the objective functions of respectively of x1, x2, s1 and s2 here. These are the coefficients. So 3, 4, 0, 0 are the coefficients respectively of x1, x2, s1 and s2. And here cv is the coefficient of the basic variables in the objective function. CBs are the coefficient of the basic variables. What are my current basic variables is S1 and S2. So this is my current basic variables, and these are the non-basic variables. So this is a body matrix and this is an identity matrix. I will tell you what I am calling it an identity matrix. And B I have represented as 450 and 600 here, the resources. Okay, so this is my first basic feasible solution and the first table that I have constructed in simplex method. So here, very importantly, you should know that these are AIJs. These are called the AIJs. The AIJs of the basic variable will be an identity matrix. So this is the first basic variable, so 1 0, and this is second variable, basic variable, so 0 1, and this is an identity matrix. This is an identity matrix. So this is my first basic feasible solution. Now, is this solution an optimal solution? We'll find it out. How to do that? We have to find out ZZ. ZZ is nothing but AIJ into CB. So here, so we'll perform the optimality test. To perform the optimality test, we have to find out ZZ. ZZ is the summation of CB into AIJ, that is 0 into 1 plus 0 into 2. It gives us 0. So again 0 into 1 plus 0 into 1 gives us 0. 0 into 1 plus 0 into 0 gives us 0. So likewise we find out all the ZZs. And we'll find out the CJ minus ZZ. So CJ is this one. CJ minus ZZ. 3 minus 0 is 3. 4 minus 0 is 4. 0 minus 0 is 0. 0 minus 0 is 0. So now, how to find out whether this is an optimal solution or not? To find out whether this is an optimal solution or not, we have to check these values, C, Z minus these values. We have to check. Now in these values, if any value is positive, then the solution is not optimal. If any value is positive, and the column having the highest value, that is this value, this becomes the pivot column, or you can say x2 is the entering variable. X2 is the entering variable, or you can say currently x2 is a non-basic variable. It will become a basic variable and will come somewhere around here. Okay, before I proceed, I want to make a point here. Now, the method that I am discussing here may be slightly different from the method that which you have learned. The way of solving may be slightly different, but what you are doing or you have done and what I am doing are same. End result will be same. It doesn't matter, your teacher might have taught you in a different way. You might have taken a ZZ minus CZ. It doesn't matter. But what we are doing are the same. So you are free to use your own method. No problem. Your understanding of revised simplex will not be affected. But here I am discussing the method which I feel is the most easiest one. Okay. So I am saying here, so this value is positive and is the maximum of all the CJ minus ZJs. So this will be the entering variable. If this is the entering variable, that is the x2 is the entering variable, it will become a basic variable. It is currently a non-basic variable. It will become a basic variable and it will replace either S1 or S2. Now the question is which it will replace. How to find out which variable it will be replacing? To find out that, we will be dividing 450 by corresponding value of Aij in the pivot column, that is 1. So that gives us theta as 450. Similarly, 600 divided by 1 will give us 600. Okay, so out of these two values, in this case, in other cases, all the values of theta, whichever is less will be the pivot row, and that variable will be the exiting variable. So in this case, S1 will be my exiting variable. S1 will be my exiting variable. So this will be replaced by this one. So x2 will become the basic variable and S1 will become a non-basic variable. Okay, now this much we have understood. How to construct the next table, how to iterate. So we will be iterating towards an optimal solution. So how to iterate? This was my previous table. Now I have to iterate and construct a new table. Now you have to understand that whichever is the pivot row, if this is the pivot row, so then the same row here in the new table will be all the aij's divided by the value of the pivot cell. The next row, this row in the next table will be all the aij's, that is 1 divided by 1, again 1 divided by this one, 1 divided by this one, 0 divided by this one, 450 divided by this one. So we get 1 1 1 0 450 here. Okay, now you might have noticed a term FR here. FR. Now what is this FR? FR is basically fixed ratio. Now what is this fixed ratio? Now my objective is to make, apart from the pivot cell, all the values in the pivot column zeros. So that means this value has to be 0. Sorry. So this value has to be 0. So in order to make this value 0, so how we find out the aij's in this next table is that we take this value and subtract it by the aij's of the pivot row into a fixed ratio. Now this fixed ratio has to be selected in such a way that in the pivot column, apart from the pivot cell, all will be 0. This has to be 0. I'll explain why it has to be 0. It has to be 0. So therefore this has to be 0. In order to make this 0, so 1 has to be multiplied by 1 itself to make it 0. So 1 minus this one minus this one into this one will give me 0. So this here it will be 2 minus 1 into 1, that is 1. Okay, so 0 already we have. So this will be 0 minus 1 into 1 will give us minus 1. So this will be minus 1. So in this case it is 1 minus 0 into 1 is 0, so it will be 1, and 600 minus 450 into 1 will be 150. Okay, so again we'll perform the optimality test in this table. So perform the optimality test. Again we'll find out the CB. See, x2 value I have replaced here. I replaced the s1. Remember this, don't forget to replace these values in the basic variable. So s1 is replaced by x2, and similarly when I am replacing the x2, the CB of x2 is 4 in this objective function. The coefficient of the basic variable in the objective function is 4, so I have written 4 here. So 4 into 1 plus 0 into 1 will give us 4. So 3 minus 4 is minus 1. It is perfectly okay. So x2 here, sorry, in this 4 into this one is 4. 0 plus 0 into 0 is 0, so this is 4. So 4 minus 4 is 0, and similarly here it comes 4, so it comes 0 here, so it's minus 4, minus 4. Now notice that in all these values there is no positive value. So therefore the solution I can say is an optimal solution. This is an optimal solution. And what is the solution? The solution is that x2 is equal to 450 and the maximum is 800 and the maximum z is 800. So that is the solution. And x1 is 0. x1 is 0. Now I want you to notice that what are the basic variables here? The basic variables are x2 and s1. So remember, I have given a statement earlier that the aij's of the basic variables in the table will be an identity matrix. So you can notice here, so in the first table, s1, s2 are the basic variables. So here, this is an identity matrix. This is an identity matrix. The aij's of the basic variables are an identity matrix. So here, so this is 1 0 and this is 0 1. So x2 and s2 are the basic variables, and if you represent x2 s2 in a column matrix, it will be 1 0 0 1. So it is an identity matrix. So my first statement is that, remember, if it is not, then you have done some mistake. Remember, this is check. So always the aij's of the basic variables will be an identity matrix, and the cj minus zj of the basic variable has to be 0. Another statement I am giving here. Remember, cj minus zj of all the basic variables has to be 0. Cj minus zj, I repeat, of all the basic variable has to be 0. So here, what are the basic variables in this table? s1 and s2. So cj minus zj of s1 s2 is 0 here. This is also 0 here. In this case, the basic variables are x2 and s2. cj minus zj of basic variables are 0 and 0 here. Sorry, and 0 here. Okay, now this is not by chance. This is not by chance. This is by design. So the table is designed in such a way that cj minus zj had to be 0, and it has to be an identity matrix. The basic variable, the aij's of the basic variable has to be an identity matrix. You can see, say this I have forcefully made 0, and accordingly I have found out the fixed ratio. The fixed ratio I have found out so that this becomes 0. When this becomes 0, this will be a part of an identity matrix. So this is not by chance, this is by design, that the aij's of the basic variables will be a identity matrix, and the cj minus zj's of the basic variable will always be 0. So this is a way we can check your solution. If these are not correct, then your solution is something wrong in your solution. So I hope you have understood the basic method of the revised simplex method. So we will conclude here in this lecture, and in the next lecture we will discuss one more problem so that the doubts of the simplex methods gets further cleared before we move on to the revised simplex method. So I thank you wholeheartedly for watching this video.